The DataFrame data structure is the heart of the Pandas library. It's the primary object that you'll be working with in data analysis and cleaning tasks. The DataFrame is conceptually a two-dimensional series object where there's an index and multiple columns of content, with each column having a label. In fact, the distinction between a column and a row is really only a conceptual distinction, and you can think of the DataFrame itself as simply a two-axis labeled array. You can create a data frame in many different ways, some of which you might expect. For instance, you can use a group of series, where each series represents a row of data, or you could use a group of dictionaries, where each dictionary represents a row of data. Let's take a look at an example. I'm going to create 3 purchase order records as series objects for a sort of fictional store. Each series has a name of a customer, a string which describes the item being purchased, and a cost to the items. I like dogs, so I'll purchase a bunch of dog food. Kevin Collins Thompson, the instructor for the 3rd course in this series, he seems more like a cat man to me, so I'll have him purchase some kitty litter. And I think Vinod, who teaches the 4th course in this series, is more of a bird man, so we'll add some bird seed there. Then we'll feed this into the data frame as the first argument and set index values indicating which store where each purchase was done. You'll see that when we print out a data frame, the Jupyter notebooks try and pretty it up a bit and print it out as a table, which is nice. Similar to the series, we can extract data using the ilock and lock attributes. Because the data frame is two-dimensional, passing a single value to the lock indexing operator will return a series if there is only one row to return. In this example, if we wanted to select data associated with store 2, we would just query the lock attribute with one parameter. You'll note that the name of the series is returned as the row index value, while the column name is included in the output as well. We can check the data type of the return using the Python type function. It's important to remember that the indices and column names along either axes, horizontal or vertical, can be non-unique. For instance, in this example, we see 2 purchase records for store 1 as different rows. If we use a single value with the DataFrame lock attribute, multiple rows of the data frame are returned, not as a new series, but as a new data frame. For instance, if we query for store 1 records, we see that Chris and Kevin both shop at the same pet supply store. One of the powers of the Pandas data frame is that you can quickly select data based on multiple axes. For instance, if you wanted to just list the costs for store 1, you would supply 2 parameters to .lock, one being the row index and the other being the column name. If we're only interested in store 1 costs, we could write this as df.lock sub store1, costs. What if we just wanted to do column selection and just get a list of all of the costs? Well, there's a couple of options. First, you can get a transpose of the data frame using the capital T attribute, which swaps all of the columns and rows. This essentially turns your column names into indices, and we could then use the .lock method. This works, but it's pretty ugly. Since ilock and lock are used for row selection, the Pandas developers reserved indexing operator directly on the data frame for column selection. In a Pandas data frame, columns always have a name, so this selection is always label-based, and not as confusing as it was when using the square bracket operator on the series objects. For those familiar with relational databases, this operator is analogous to column projection. Finally, since the result of using the indexing operator is a data frame or series, you can chain operations together. For instance, we could have rewritten the query for all store 1 costs as df.lock sub store1 sub cost. This looks pretty reasonable and gets us the result we wanted. But chaining can come with some costs and is best avoided if you can use another approach. In particular, chaining tends to cause Pandas to return a copy of the data frame instead of a view on the data frame. For selecting a data, this is not a big deal, though it might be slower than necessary. If you are changing data, though, this is an important distinction and can be a source of error. Here's another method. As we saw, .lock does row selection, and it can take 2 parameters, the row index and the list of column names. .lock also supports slicing. If we wanted to select all rows, we can use the colon to indicate a full slice from beginning to end, and then add the column name as a second parameter as a string. In fact, if we wanted to include multiple columns, we can do so in a list, and Pandas will bring back only the columns we've asked for. Here's an example where we ask for all of the name and cost values for all stores using the .lock operator. So that's selecting and projecting data from a data frame based on row and column labels. The key concepts to remember are that the rows and columns are really just for our benefit. Underneath this is just a 2-axis labeled array, and transposing the columns is easy. Also, consider the issue of chaining carefully and try to avoid it. It can cause unpredictable results, where your intent was to obtain a view of the data, but instead Pandas returns to you a copy. In the Pandas world, friends don't let friends chain calls, so if you see it, point it out and share a less ambiguous solution. Now, before we leave the discussion of accessing data in data frames, let's talk about dropping data. It's easy to delete data in series and data frames, and we can use the drop function to do so. This function takes a single parameter, which is the index or row label, to drop. This is another tricky place for new users to Pandas. The drop function doesn't change the data frame by default, and instead returns to you a copy of the data frame with the given rows removed. We can see that our original data frame is still intact. Let's make a copy with the copy method and do a drop on it instead. This is a very typical pattern in Pandas, where in-place changes to a data frame are only done if need be, usually on changes involving indices, so it's important to be aware of. Drop has 2 interesting optional parameters. The first is called in-place, and if it's set to true, the data frame will be updated in place instead of a copy being returned. The second parameter is the axis, which should be dropped. By default, this value is 0, indicating the row axis, but you can change it to 1 if you want to drop a column. There is a second way to drop a column, however, and that's directly through use of the indexing operator using the del keyword. This way of dropping data, however, takes immediate effect on the data frame and does not return a view. Finally, adding a new column to the data frame is as easy as assigning it to some value. For instance, if we wanted to add a new location as a column with the default value of none, we could do so by using the assignment operator after the square brackets. This broadcasts the default value to the new column immediately.